CRF for hosting this event. This is my first in-person meeting in the last 3 years. So I really appreciate this opportunity. Last weekend I was watching the Oscars, and I think the best joke was the first one, that the 3 ladies that were the hosts of this event said that the Oscars hired them because they cost less than 1 guy. And I certainly support the notion of pay equity, and I actually think it's opposite. I think it takes 3 guys to match the performance of 1 lady. So it's a very, very tough act for me to follow the 2 ladies. I think it would take 6 of me to match them. Anyways, a normal adult in the Western world consumes about 1 million calories a year. So it takes a lot of careful auditing in the brain to match the output with the intake. So as is often the case, at least with me, we have a problem with eating too much and exercising too little, leading to obesity. But today I'm more interested in the opposite, when we don't eat enough and we expend too much in energy, leading to the conditions of malnutrition and cachexia. So I like to give you some examples of malnutrition and cachexia in some celebrities that we know. The first one is Christian Bale. He is known to transform his body dramatically in different movie roles. The first one is The Fighter, when he loses, I don't know how many pounds, to portray a drug addict, for which he won the Oscar for supporting actor. Then he ate and didn't exercise and put on a ton of weight to play ex-Vice President Dick Cheney. And then in between, he shaped up and played his multi-million-dollar role as the Batman. So you can transform your body by eating more, eating less. And obviously exercise is an important component of that. And cachexia is a condition that is not reversible. Unfortunately, this is Steve Jobs in his healthy self on the left. And then at the end of his life, when he had pancreatic cancer, he had cachexia, from which he never recovered, and during which time he experienced extreme muscle wasting. So we actually look at the pathophysiology of these 2 conditions. They are actually very, very different. The only commonality is a negative energy balance. They don't eat enough. Or there's no balance between the intake and the output. In the case of malnutrition, it's very physiologic. So if you don't have enough, then you want to eat more. You have a good appetite. You slow down your metabolic rate in order to preserve your body composition. You preserve your muscle mass at the expense of losing fat mass. And once you give calories back, it bounces back to normal in a very short space of time. Whereas in cachexia, despite the negative energy balance, you don't really want to eat. You're anorexic. Maybe it's due to problem with swallowing, maybe not. And then you still have a high metabolic rate, and we still need to understand why that is, why you spend so much despite not having enough. And then you have muscle wasting. You don't have a good muscle mass. And then when you give calories back, your body just puts on more fat mass and don't gain your muscles so readily. Cachexia is a problem in a lot of chronic diseases such as cancer, COPD, chronic infections such as HIV infection, but it is also a problem in chronic kidney disease. It is very prevalent, up to 75% in patients on dialysis. And the phenotype of cachexia actually is a prognostic value in terms of their survival. The first one is anorexia. Patients with kidney disease are anorexic. This is an interesting study done in UCLA by my friend Kalantar Zaye, and what he did was he asked 400 dialysis patients one simple question: what is your appetite? If your appetite is good, then the outcome is very good. If your appetite is bad, then the outcome is significantly worse. The other one that's obvious is loss of protein stores or muscle wasting. There are some surrogate markers of muscle wasting, which is kind of not easy to quantitate. So serum albumin has been used as a surrogate marker. And this is a study in kids showing that in kids on dialysis, if you have a normal serum albumin, then your survival is 3-4 times better than when you have abnormal serum albumin. And then, as I said, increased energy expenditure is a maladaptive feature of cachexia. My friend Angela Wang in Hong Kong, she did this study looking at adults on peritoneal disease, and basically people who have more or less energy expenditure have survival rate, whereas those with high energy expenditure, they don't. So that was a good point for me to describe one of my favorite topics, white and brown fat. So most people know about white fat. That's what makes you obese. But there's also another category of fat called brown fat. So it's like brown rice and white rice. Brown is usually the healthy part. So the brown fat is actually around the shoulder region. And the major difference is that brown fat actually uses energy, is an energy organ, whereas the white fat is a storage organ. So it has a lot of enzymes characterized by UCP1 that burns energy in forms of heat. So there's brown fat and there's white fat. White fat is one big globule of fat, which is a storage energy. And there's only a couple of like mitochondria, whereas in brown fat, a lot of mitochondria are much smaller, steeple. And the intermediate is what we call beige fat, which is intermediate between white and brown. So phenotypically, there's one feature that distinguishes between brown and white is the presence of this enzyme UCP1. And as I said, there's a lot of mitochondria in brown, multilocular in brown, and brown burns energy and white stores energy, and then beige is in between. So, so is brown fat almost always good for you? I'm actually learning how to speak as a lawyer because my son is starting law school. So the answer is it depends. So in healthy people, yes, if you have a lot of brown fat, you tend to stay slim. And as a result of brown fat, you also produces heat. So a lot of times when you see lean people, they look good, they describe as being hot. So that may be the reason. But there's also an interesting phenomenon in disease conditions, especially cachexia. There's a transition of white fat to brown fat. So the white fat is usually a storage organ, actually in pathological conditions, can actually be turned into brown fat, that they burn of energy in an inappropriate situation and loses body weight. And also interestingly, both muscle, white, and brown fat can actually all be derived from the stem cell. So there is some system in the body that controls the final fate of the stem cell, whether it develops into a muscle, a white fat cell, or a brown fat cell. So in conditions of muscle wasting, maybe that is the switch from muscle, maintaining muscle mass to developing other body mass such as fat or brown fat. And there's also what we call a trans differentiation of white into brown, which is not good in conditions of cachexia. So back to cystinosis. You've seen this picture before. Multi-system involvement and a high incidence of myopathy, up to 70% in long-term studies. And thanks to Dr. Cherqui, we have this mouse model of cystinosis by knocking out this cystinosin gene. And the mouse model, the phenotype of this mouse closely resembles that of the clinical situation with kidney failure and muscular abnormalities. So we obtained funding from the CRF about 10 years ago, and we've undergone a series of investigations, and we published those in good journals. And I want to give a little shout out to the journal Cachexia. We formed the Society of Cachexia about 16 years ago, and they have produced a very high impact journal, the Journal of Cachexia. I sent all my best papers to them, and I published 3 from my work with the CRF. So the first one is describing the phenomenon of muscle wasting and fat browning in this mice with cystinosis. So if you can look at this, this is normal muscles, this is size muscles, this is muscles with kidney failure, and this is muscles with cystinosis. So the muscles from cystinosis mice are even smaller than the muscles in with just kidney failure. So very severe muscle wasting. We did muscle function tests. I don't want to belabor you with all the detailed tests that we can do in humans, but this is how we do it in mice. This is grip strength. We let the mouse hang onto this grid, and we pull their tail until they let go. And this is rotor rod activity. We put the mice on a rotating rod, and then we time them to see how long they can stand on this device. And we show that the black is CTNS, the white is normal, and the gray is the mice with kidney failure without cystinosis. So the cystinosis did the worst. And then fat browning, as I mentioned before, UCP1 is an enzyme that characterizes brown fat. So this is 4-month healthy mice, 4-month CTNS mice, already a fair amount of browning. At 12 months, severe browning, even more than that of a mouse with just kidney failure. And then we switched to vitamin D. It's one of my favorite subjects. So the vitamin D is usually, that we usually talk about 2 metabolites. Dr. Grimm has given a very good talk yesterday. So 25D is the main circulating vitamin D. It's the best indicator of vitamin D status because it's 1,000 times higher in concentration than the 125. And the half-life is also much longer. So this, the 25 is the more important metabolite. Although in kidney failure, the main problem is the 125. As far as muscle is concerned, vitamin D is important because there are vitamin D receptors in muscles. So the vitamin D status actually is important in maintaining muscle strength. So with age, there's a decrease in the abundance of vitamin D receptors in skeletal muscle, which is why that physical performance and vitamin D levels correlate with each other in older individuals. I take vitamin D supplements myself. And then we found that there is profound vitamin D deficiency in cystinosis mice, and when we gave the vitamin D back, it corrects their muscle wasting and fat browning. So as you can see, this is the CTNS mice, very small muscle cells, and we give both 25 and 125 back. They almost normalize, or they much improved. So Dr. Grimm has talked about this yesterday. So we make vitamin D from exposure to sunlight. It goes into the liver, becomes 25D, and has to go through the kidney to become the active compound 125D, which then goes to the bones to help us maintain healthy bones. But in the recent years, it's been discovered that this specific enzyme in kidney that converts the 25 into the active 125 is also present in muscle. So you don't need the kidney to maintain normal vitamin D in muscles. You only need 25. So 25 is more important as far as I'm concerned for muscle health. So we did this more recently to compare 25 versus 125. And make the long story short, it's a complicated slide, but 25 almost normalizes the muscle wasting and the fat browning, irrespective of 125, because there's a local factory in the skeletal muscle to generate your 125. So maintaining 25 levels is more important. This is just more, yeah. So we've actually done some what we call RNA sequencing, look at all the genes involved in muscle metabolism, and we show that the vitamin D is very important, including those involving the satellite cells that was mentioned in the last talk. So the muscle regeneration by the satellite cells are much improved when you replenish the vitamin D. And then our latest research is into inflammation. We started off targeting interleukin-1, IL-1, and we look at this compound because there's already an FDA-approved compound to counteract IL-1, which is anakinra. So this anakinra has been approved for treatment of rheumatoid arthritis for 15 years already. So there's a lot of experience using this compound, and potentially can be repurposed for other conditions such as cystinosis. So we did this and was published last year, and basically improves muscle wasting and also improves fat browning. And again, we did RNA sequencing, and everything is improved. It reverses cachexia, it decreases inflammation, it lowers the energy expenditure to normal, it reverses adipose browning, muscle wasting, and all these other metabolic pathways, including the satellite cell muscle regeneration. So this is a very promising compound. And this is a picture of Hal Hoffman, a very eminent scientist in UCSD. His claim to fame was he cloned the pathway that leads to the production of IL-1, which is the pathway called NLRP3. He discovered this in autoimmune diseases, and he's identified the various components of the NLRP3. And we've actually identified that all these various steps, all these various molecules in the NLRP3 inflammasome pathway has been upregulated in the muscles in the cystinosis mice. And the other development is that this NLRP3 is now known to be important in various diseases apart from these autoimmune diseases. It's important in obesity, fatty liver disease, and even heart diseases. So it turns out that NLRP3 is a very important role to play in heart disease, like myocardial infarction, stroke, and so on. And more recently, interesting enough, is also thought to play a role in COVID infections. It's actually been used in some severe COVID infections and thought to actually improve the situation. So since it involves so many organs, the NLRP3 and so many organs are involved in cystinosis, we did a survival study. So this is normal mice, and this is CTNS mice, the cystinosis mice. And if we knock out the components of the inflammasome, it significantly improves survival. So this is very promising. And whilst I'm on muscle, I also want to draw your attention to this study. This is called the PURE study, which is almost like an international Framingham. They took 150,000 normal individuals in all the continents and followed them prospectively for 10 years. And there's only one measure, grip strength, that predicts all-cause mortality and the incidence of myocardial infarction, stroke, and other diseases. So the presence of good muscle strength and the lack of inflammation portends long life. With this, I want to end. I want to thank the CRF for supporting our line of research in this area. With the preliminary studies from the CRF, we're able to obtain funding from the NIH about a year and a half ago, and NIH being reviewed in a few months concerning cystinosis. And then our research is also supported by the Muscle Center grant given to UCSD. We actually also have an NIH T32 training grant. So a lot of our fellows go through my lab and they do this research supported by NIH. And some of them have actually gone on to win both regional and national research awards. So I'm very thankful to all my collaborators, especially to CRF for funding our research. Let's stop here and entertain any questions you may have.